Hello everybody and welcome back to another video. In this video we're going to start sections 9.2 and 9.3 on exponential and logarithmic functions. To begin, let's just go ahead and define exponential functions. So the function f of x is equal to a to the x. That's what it will look like. That's our exponential function where a is a positive constant, a does not equal 1, and x is any real number. That is called an exponential function with base a. Let's break that down a little bit more just to be clear why we have these special stipulations. Well, we demand that a is a positive constant, so that way we don't have a zero function, because if a were 0 we'd get 0 to the x. That's just 0. That's not interesting. And also if a were negative, then we would go into the complex world dealing with imaginary numbers, which we don't talk about too much in this course. So that's why we insist that a is a positive constant. And also we insist a does not equal 1, because then you get 1 to the x. And the function f of x is 1 to the x is really just f of x equals 1, because if you take 1 to any power, you're still going to get 1 back. So that's why we have that extra stuff. So that these two right here, y equals 2 to the x and y equals 1/2 to the x, these are both examples of exponential functions. So let's pan over to the side for a moment. One thing I said is that x can be any real number. So in other words, we can raise any positive constant not equal to 1. We can raise any positive constant not equal to 1 to any real number that we'd like. Let's see what this means in practice. So let's just say, let's start with integers. So if we have an integer exponent, it's very straightforward. If we have like 5 to the third, we know what that means from before, from way back in section 1.6. We know that 5 to the third means 5 times 5 times 5, which is 125. So here, when it's an integer, it's just repeated multiplication. But let's say it's a rational number. What if it's 5 to the 3 over 4? Then, well, we know what to do in this situation too. We learned about this previously as well. Whenever you've got a rational number exponent, we can convert it into a radical expression in the following way. We can write it as 5 times 5 times 5. We're still going to have that part of it because it's still 5 to the third, but we're raising it to the, we also got this 4 in the denominator, so it's really like 5 to the 3/4, so we have to take the 4th root. So I'll put in my radical, and the index is 4. So we're taking the 4th root of 5 times 5 times 5. Or in other words, the 4th root of 125, if you like that better. So in either case, when we had an integer, when we had a rational number, it was fairly straightforward, but let's suppose we've got something a little bit more general. Let's suppose we've got an irrational number. So for an irrational number, it turns out that we can't, that this still has a meaning, but its meaning is basically just an approximation. So here's what I mean. We know that the square root of 2 is approximately like 1.4 something, okay? So what we would do is we would take 5 to the 1.4 ... and we would basically just keep adding on more digits of precision to get a closer idea of what this actually equals. I probably should have calculated what this is prior to making this video, but if you're curious, go ahead and calculate this and see about approximately what you get. But anyway, all of this is just to show that we can take any real number as our exponent and still get something that's well defined. So we did integers, rational numbers, and even irrational numbers, and ultimately that covers all the real numbers. So next, why don't we look at some pictures of exponential functions. Let's look at this picture on the left first. We've got to graph it, but we've got the function y equals 2 to the x. Well, it's going to look something like this. It's going to have a shape that opens up like this. And notice that as you move to the left, it gets closer and closer to the x-axis. That's called a horizontal asymptote. Every exponential function has a horizontal asymptote. So we have a horizontal asymptote, that's the x-axis, but don't worry too much about that language. And then y equals 1/2 to the x looks something more like this. So try to draw this as best as I can. Something like this. So, something that's peculiar, something to point out with these two pictures, is that if we rewrite this 1/2 to the x, if we rewrite this as 2 to the -1 to the x, that's actually the same exact thing as 2 to the -x. We multiply in the exponents in that situation, right? So we get 2 to the -x. Well, the only difference between y equals 2 to the x and y equals 2 to the -x is that one is a mirror image of the other. They're mirror images of each other, rather. So here's what I mean. If we take this function y equals 2 to the x right here, and we were to reflect it over the y-axis, we get this graph. And if you've seen transformations of functions, this is more obvious, but if you haven't noticed, that's what, in effect, that's what happens when you substitute in -x for x. You reflect over the y-axis. So I think that's it for this video. In the next video, we're going to continue on and we're going to get into logarithmic functions, and we're going to talk a bit more about the relationship between exponential and logarithmic functions. So I hope this video was helpful, and we'll see you all in future videos. Have a great day.